Deepseek V4 has just been released. It adopts a rather complex attention mechanism. The goal is to squeeze out maximum performance to better support long contexts. Today we'll explain Deepseek's attention from V2 to V4 to understand how it maximizes performance and pushes towards longer contexts. First, let's talk about the motivation. We know that long context is becoming increasingly important. For example, we now have coding agents like Claude Code. These agents can operate autonomously for extended periods of time to carry out a task. So we've moved from simple single-turn conversations to long-running operations. During this process, the model will output its own thoughts, call tools, and generate more and more tokens. As a result, our context becomes longer and longer. This increasing context length poses a serious challenge to our systems. Let's first review what components a computer system has. It mainly consists of compute, storage, and communication. But in long context, this challenges attention mechanisms, both computationally and for storage. Computationally, attention has quadratic complexity, so as the context gets longer, computation here skyrockets. On the other hand, we need to store the KV cache for all past tokens. The total size of the KV cache is linearly proportional to the context length. However, accelerators such as GPUs and TPUs have limited storage units like HBM. So when the context becomes longer, whether we can store all this past history becomes an issue. To alleviate the pressure on both computation and storage, Deepseek V4 has proposed two attention algorithms. These algorithms save on attention computation and KV cache storage with different focuses. Among them, CSA, compressed sparse attention, moderately compresses the storage of the KV cache, but it greatly reduces the computation required for attention. The other attention, HCA, heavily compressed attention, compresses the KV cache much more, but its attention remains fully dense. To understand the details of these two attention mechanisms, it's necessary for us to review how Deepseek's attention mechanism evolved. In standard multi-head attention or grouped query attention, all tokens must be processed to get an attention score for each pair of tokens. And the model dimension is the same between the KV cache and the input embedding. In Deepseek V2, the KV cache has been compressed, which alleviates storage pressure. Then Deepseek V3.2 introduced Deepseek Sparse Attention, or DSA, which rates the importance between query and key. For each query, we only attend to the keys with the highest scores. DSA in 3.2 was based on MLA, so it performs both KV cache compression and sparse attention. Finally, we have the current Deepseek V4, which was also based on MLA, but it further compresses multiple KV cache tokens into a single entry. In addition, it introduced hybrid attention. Some layers compress the KV cache more aggressively, while others perform fewer attention calculations. Now, we'll explain MLA, DSA, and hybrid attention in V4 in detail. MLA, or Model Head Latent Attention, reduces the size of the KV cache by compressing its model dimension to a smaller one, which is essentially a low-rank tensor. This diagram shows the entire computation process. The model's input is an embedding with the shape BTD, where B is the batch size, T is the sequence length, and D is the model dimension. The blue and the red parts here represent the compression of the query and the KV cache, respectively. We compress the query's model dimension to a compressed dimension C. Then it is split into two parts. One part is the content query, and the other part is the rope query. The content query does not have positional encoding added to it. The positional encoding is only added to the tensor in the second part. Both the content query and the rope query are multi-headed. We can see their tensor shapes, batch size, sequence length, n, the number of heads, and h, the per head model dimension for the content query. The rope part consists of a separate rope dimension, r. The content query and the rope query are combined to form the complete query. We'll explain why we decouple content and rope soon. Roughly speaking, positional encoding is incompatible with MLA, so it's applied separately. Next, let's look at the key and the value. The first part is the same. We reduce it to a lower rank C. After that, we project them to multi-head key and value. The positional encoding for the key is handled differently from the query. It comes directly from the embedding. Then this step is similar, where we concatenate the content key and rope key. Since we have the query, the key, and the value, we are able to perform standard QKV attention. During this process, we will cache the compressed KV and the rope key. This approach can greatly save storage, because the C in our BTC dimensions is very small, and rope is only applied to a part of the model dimension. Let's see why rope is handled separately and is incompatible with MLA. We'll break down the formulas step by step. Consider the case without rope. We calculate the attention score by multiplying matrix Q with the transpose of K. Q is the product of two matrices, a compressed query and a matrix that restores Q's dimensions. Let's go back to the diagram above to see what's going on. Here is the input embedding whose model dimension is D. It is projected onto a lower rank, that is dimension C. This tensor is the CQ matrix we just saw. That is right here. Then we turn it into a content query by restoring its dimensions and converting it to a multi-head tensor. Here, N is the number of heads and H is the per head model dimension. The transformation from BTC to BTNH is realized by the upper projection for Q. Similarly, K is a product between the compressed CKV and the upper projection for K. When expanding the transpose for K, we need to swap the order of the two matrices. W is placed in the front and C is placed at the back. By using the associative property of matrix multiplication, we can combine this UQ and the transpose of UK into a single matrix. Then during inference, we only need to cache the compressed KV tensor without explicitly expanding it and computing a WUK multiplied by CKV. If we add positional encoding, specifically rope, the situation changes. Rope is a relative positional encoding that multiplies the original tensor by a rotation matrix R, causing the angle of this tensor to change. Similarly, K will also be multiplied by another rotation matrix. Now, when expanding the transpose, the rotation matrix RK is placed at the front, and the product of RQ and RK represents the relative angle between the query and the key, which is related to their relative distance. In other words, the rotation matrix is not a constant. And this matrix separates the two matrices we want to merge so they can't be combined into a single constant matrix. That's why we need to handle the rope part separately. Now let's quickly review MLA. It introduces low rank compression, which reduces the size of the KV cache. Additionally, it introduces the decoupled rope technique, allowing us to fuse matrices and only cache the compressed tensor. So Deepseek v2 mainly focuses on how to reduce storage, without much optimization for attention computation. Next, let's take a look at Deepseek sparse attention, introduced in Deepseek 3.2, which simplifies the computation of attention. For a given query, it does not attend to all previous KVs and compute relevant scores. Instead, it selects only a subset. DSA is based on MLA, so its flowchart is similar, except for the additional green section. The green section mainly contains two boxes. The first is called the lightning indexer, and the second is the top K selector. In the first box, the query scores all past keys in order to find the most relevant ones. Then the second box selects the top K keys for attention calculations and skips the rest. So, what the lightning indexer essentially does is assign an importance score to every pair of tokens. Now, how is this score determined? Actually, what we really want is the attention score obtained by multiplying the query and key. But if we calculate the attention score directly by multiplying Q and KT, then there would be no need for this scorer. Therefore, the computation here must be lightweight, fast, and computationally efficient. Specifically, we further project the query compression in MLA to obtain a multi-head query and apply partial rope to its last few dimensions. The key is shared across all query heads, and the last few dimensions of the key also have rope applied. Multiplying this multi-head query by the shared key yields token relevant scores. You might think that the amount of computation here seems similar to that of actual attention. But actually, both the query and key are quantized to fewer bits, and a faster ReLU activation function is used. As a result, the amount of computation is reduced. One last arrow remains, the per head gate weighting each query head for a combined weighted sum. We'll skip the specific math due to the time limit. In summary, DSA changes from computing attention scores over all previous tokens to selecting only the K most important tokens. In addition, with the integration of the MLA KV compression, both compute and storage have been optimized. Finally, let's talk about Deepseek v4. Here, the KV cache compression dimension is different. Previously, we compressed along the hidden dimension, but in v4, the compression is done along the token dimension, or in other words, the sequence dimension. v4 introduced two types of attention mechanisms, CSA, also known as C4A, and HCA, also known as C128A. As the name suggests, C4A compresses every 4 tokens into a single entry. C128A is even more aggressive. It compresses every 128 tokens into one entry. In this C4A with a relatively small compression rate, we use DSA Deepseek sparse attention, which was introduced in v3.2. Now, let's take a look at the diagram for CSA. We compress input activations 4:1 into KV entries using v3.2's top K selector to keep only the most important tokens. In addition to these two types of attention, we can also see sliding window attention. It is to prevent the loss of key information that might occur during the 4-in-1 token compression. Therefore, it performs attention calculations on uncompressed tokens. However, to reduce computation, it uses local attention, meaning it attends only to the previous 128 tokens rather than all past tokens. Looking at HCA, it combines 128 tokens into one entry, which happens in the token level compressor. HCA doesn't have a top K selector. This is actually a kind of trade-off. Here, we've compressed the KV a lot, so the attention computation is fully preserved. Additionally, HCA also has a branch that uses sliding window attention. CSA and HCA are used in a hybrid manner. Some layers use the CSA method, which applies moderate KV compression but utilizes sparse attention, along with a sliding window. Other layers use much more aggressive KV compression but employ full attention, also combined with a sliding window. The combination of these two approaches achieves a good balance. That's all for today. Thanks for watching. If you enjoyed this, please like and save. See you next time.